derivatives of trigonometric functions and higher order derivatives. We saw in the previous section the derivative for cosine was negative sine and the derivative for sine was cosine. So here we add the other four, that the derivative of tangent is secant square, the derivative of cotangent is negative cosecant square, the derivative of secant is secant tangent, and the derivative of cosecant is negative cosecant cotangent. Now, the way that you remember the negatives, like I said before, if you take the derivative of a trig function and that term starts, the function starts with a c, like cotangent, cosecant, cosine, the derivative, the result is always a negative. Now, in terms of trying to memorize what these derivatives are, is not bad at all. When I was in school, we had to actually prove these derivatives, and once you prove them, you never forget them. But you definitely want to commit them to memory. I have. So we'll start with number 39. Find f prime of t. This is the product rule. Take the derivative of the first, so that's 2t times the second plus the first times the derivative of the second. That's it. Now you can factor out a t from both of these, and write this as t times parentheses 2 sine t plus t cosine t. Here we make use of the quotient rule. This cosine t and that t have nothing in common. So this is f prime of t is equal to the derivative of the numerator is negative sine t. This is times the denominator minus the numerator cosine t times the derivative of our denominator, which is just 1. And that's all over our denominator squared. So you can simplify that. This is f prime of t, if there is any simplification. So we write this as negative t sine t minus cosine t all over t squared. So here for this one, f prime of x is equal to the derivative of negative x, which is just negative 1, plus the derivative of tangent x is secant squared x. This derivative, we say g prime of t. Well, you know that this term here is t to the 1/4. So this is 1 over 4 times t to the 1/4 minus 1. So this is negative 3/4 minus, and I'm putting a minus because I know that the derivative of cosecant is going to be a negative. So this is the 6 there, and the derivative of cosecant is cosecant t times cotangent t. Now you can fix that up, if you will, and write this as 1 over the 4 times t to the 3/4 minus 6 times cosecant times cotangent t. Here, let's write this as 3 minus 3 sine x all over 2 cosine x. So y prime is using the quotient rule. That's the derivative of the numerator, which is negative 3 cosine x, times our denominator, 2 cosine x, minus our numerator, 3 minus 3 sine x, times the derivative of our denominator, which is negative 2 sine x, all over our denominator squared. Now we simplify. We have y prime is equal to negative 6 cosine squared x. This negative and that negative is positive, so say a positive here. And I'm going to distribute this 2 sine x to this term there. So let's just write it like this first so I don't throw you off. This is 2 sine x times that 3 minus 3 sine x all over 2 cosine squared x. Now I'm going to go ahead and lose the 2. I'm just going to factor out a 2 from the numerator and cancel out that 2. So that leaves me with a negative 3 cosine squared x. Plus, now I'm just distributing that sign through the parentheses, plus 3 sine x minus 3 sine squared x all over 2 cosine squared x. So here, y prime, well, it's supposed to be, is, I'm going to write this as 3 sine x minus 3 times parentheses cosine squared x plus sine squared x. Did you get that? Factor out a minus 3 from this term and that term. That leaves us with 1 cosine squared plus sine squared over 2 cosine squared x. So this is, leave this as our final answer. It's interesting. It's 3 sine x minus 3, and you can write this as 3 times parentheses negative 1 plus sine x over 2 cosine squared x. I was looking at the result compared to what we started with. Very similar pattern. Here, find this derivative. The derivative of the cosecant, again, is negative, so negative times negative is positive. This is cosecant x times cotan x, minus the derivative of the sine x is cosine x. We find this derivative. We use the product rule on this and use the product rule on this term. So it's the derivative of the first, which is just 2 times the second plus the first times the derivative of the second, and plus x squared cosine x, the derivative of the first is 2x times the second cosine x. We're going to go ahead and put the minus there because that derivative of the cosine is going to be negative sign. So it's plus the first x squared times the derivative of the second, which is negative sine x. Now, can we simplify that? Obviously, you can factor out a 2, but notice here that these two terms here can be combined. So this is 2 sine x plus 4x cosine x minus x squared sine x. The quotient rule. Oh, no, not the quotient rule. Trigonometric functions. Oh, let me make mention of the higher order derivatives. For the higher order derivatives, you can find not just y prime, the first derivative, but you can find the second, third derivative, and you can keep on, fourth derivative and so on. The first derivative gives us the velocity function. The second derivative gives us the acceleration function. In the various notations that we use for the first derivative, you may say y prime or f prime of x or dy over dx, or the derivative of the function with respect to x, or the differential operator, capital D. The operator of D, the differential, the derivative, wants to operate on y with respect to x, and likewise for the second, third, and fourth derivatives, and so on to the nth derivative. You can keep on going. Now, why is that necessary? It is possible to deal with a finite dimensional vector space, but it's also plausible to consider an infinite dimensional vector space in terms of the dimensions of certain spectrums in galaxies far beyond our galaxy. What pattern, what fundamental concept would you use, a framework, to be able to calculate and associate our atmosphere and the foundation, the mathematical foundation of the Earth and our universe in comparison to other universes and galaxies out in space? The possibility is infinite. Well, here we talk about the nth derivative, but it's possible to even deal with derivatives of infinity. I'm going to leave it at that. Thank you.